There is a planet buried inside the one you're standing on right now. Not metaphorically, not as a figure of speech. Two continent-sized masses of rock, each twice the mass of the Moon, are sitting nearly 2,000 miles beneath your feet, and growing evidence says they are not Earth. They are the leftovers of a world that died before our planet had even finished forming. A world most people have never heard of. A world called Theia. For 50 years it was a name in a textbook footnote. A convenient explanation for where the Moon came from, with zero physical proof. No fragments, no debris field, no wreckage anywhere in the solar system. Scientists needed Theia to exist for the math to work, but they had never found a single piece of it. That changed, and what they found wasn't floating in space. It was underneath us the entire time, which means the story of how our world was born isn't finished. It's still going on, right now, several thousand kilometers beneath your house. The problem nobody could solve. To understand why this discovery mattered, you have to go back to a question that quietly bothered planetary scientists for decades. Why does the Moon look the way it does? The Moon shouldn't exist in its current form. It's far too large relative to Earth. No other rocky planet in the solar system has a moon anywhere close to this size in proportion to itself. Mercury and Venus have no moons at all. Mars has 2 lumps of captured rock a few miles across. Earth has a companion nearly a quarter its diameter, locked in a tight, stable orbit. By the ordinary rules of how planets form, that shouldn't have happened. And the composition makes it stranger still. When Apollo astronauts brought lunar rock back to Earth, geologists ran isotope analysis, expecting to find a leftover chunk of primordial solar system material, something chemically distinct from Earth, the way a comet or a captured asteroid would be. Instead, they found the opposite. Moon rock is almost a chemical twin of Earth's own mantle, down to isotope ratios so similar that some early researchers assumed contamination in the lab. But there was one enormous exception: iron. Earth has a massive iron core, roughly a third of the planet's total mass. The Moon has almost none. Whatever process built the Moon out of material that looked exactly like Earth's mantle also managed to leave nearly all the iron behind. That's not a small detail, that's a fingerprint. By the mid-1970s, 2 separate research teams, working independently, using nothing more than these chemical clues and orbital mechanics, converged on the only explanation that fit all of it at once. Early Earth wasn't alone. A second world, roughly the size of Mars, had been sharing our orbital neighborhood since the solar system's earliest days, and about 4.5 billion years ago, gravity finally brought the two of them together. Not a graze, not a near miss. A direct, planet-ending collision, delivered at an angle just glancing enough to avoid vaporizing both worlds outright, and just violent enough to explain everything the rock samples were showing. They named the impactor Theia, after the Greek titan who was mother to Selene, goddess of the moon. Poetic. But naming something isn't the same as finding it. For 50 years, Theia was a ghost, required by the equations, invisible to every instrument pointed at the sky, with not one confirmed fragment anywhere in the solar system to prove it had ever existed at all. 40 years to build a moon. Here's the part that should stop you cold. Simulations suggest the moon didn't take millions of years to form, the way most planetary bodies do. Some of the newest models put it at as little as a few decades, the debris from the collision coalescing into a sphere in a time frame a human being could live through, start to finish. Picture the sequence in order. Theia, roughly Mars-sized, closes in on the young Earth at a relative speed of several kilometers per second, fast enough to cross the distance from New York to Los Angeles in under 10 minutes. It strikes at a grazing angle rather than head-on, which turns out to matter enormously. A direct hit would likely have shattered both worlds into an asteroid field, while a glancing blow does something stranger. It partially melts both bodies and flings a curtain of vaporized rock and molten debris into orbit, material from Earth's outer layers and material from Theia, sheared off and mixed together in a spinning, incandescent disk. Inside that disk, ordinary physics takes over. Gravity pulls the debris toward itself. Clumps form. Clumps collide and stick. Within an astonishingly short window, The clumps have swept up nearly everything in the disk and pulled themselves into a single sphere, settling into orbit around the wrecked planet it came from. Meanwhile, the Earth left behind is unrecognizable. Global oceans of magma cover the surface. The impact very likely knocked the planet's rotation axis into a new tilt and dramatically shortened the length of its day. Some estimates suggest the earliest post-impact days lasted only a handful of hours. This is the planet you live on, moments after it was violently reborn. But the question that lingered for decades wasn't about the moon at all. The moon, at least, was sitting right there in the sky, available for study. The real mystery was Theia. If a Mars-sized planet slammed into Earth hard enough to melt both worlds, where did the rest of it go? A body that large doesn't simply vanish. The blobs nobody could explain. The answer was hiding in a place nobody thought to look: seismology. You can't drill to the center of the Earth. The deepest hole humans have ever bored is barely 7.5 miles down, a scratch on the surface of a planet nearly 8,000 miles wide. So geophysicists do the next best thing. They listen. Every large earthquake sends vibrations rippling clean through the planet, and those waves change speed and direction depending on exactly what material they pass through. Denser rock speeds them up, less rigid or chemically different material slows them down. By recording the same quake at seismic stations all over the globe and comparing arrival times, scientists can build something like an ultrasound image of the Earth's interior. It's called seismic tomography, and it's how we know anything at all about what's beneath the crust. Back in the 1980s, using exactly this method, geophysicists noticed something odd. In two enormous regions, one beneath the African continent, one beneath the Pacific Ocean, seismic waves slowed down in a way they shouldn't have. Something down there was different. Denser in places, less rigid in others, and chemically distinct from the ordinary mantle rock surrounding it. These regions are called large, low-velocity provinces, or LLVPs. They sit roughly 1,800 miles below the surface, right where the base of the rocky mantle meets the molten outer core. And they are not small. Each one is estimated to hold roughly twice the mass of the moon. If you melted just one of them down and spread it in an even layer across the entire surface of the Earth, oceans included, it would form a shell about 60 miles thick, more than 7 times higher than the cruising altitude of a commercial airliner. For 40 years, nobody could explain what these things were or how they got there. Leading theories treated them as some kind of ancient, unusually dense pocket of primordial mantle rock that had simply never mixed with the rest, chemically odd, but native to Earth. They just sat in the seismic data, unexplained, while an entire generation of geophysicists built careers around a mystery they couldn't close. The connection came almost by accident. A geophysicist named Yuan was sitting in a seminar on planet formation, listening to a colleague explain the giant impact hypothesis. The professor mentioned, almost in passing, that the moon is unusually rich in iron relative to its size, and that nobody had ever found where the impactor, Theia, had ended up. Yuan had spent years studying the mantle blobs from the geophysics side, without a satisfying origin story for them. In that seminar, the two unrelated mysteries collided in his head. What if the blobs weren't some exotic mineral formation that had always been part of Earth? What if they were Theia, the iron-rich remains of the impactor, sunk to the bottom of the mantle and sitting there, essentially undisturbed, for 4.5 billion years? It sounds almost too simple to be the answer to two 40-year-old mysteries at once, but an idea that simple still has to survive the physics, so an international, multidisciplinary team built out full simulations to test it properly. They modeled several plausible versions of Theia's internal composition, different core sizes, different iron content, and then ran the giant impact itself, tracking how material of different densities would behave inside a molten, churning early Earth in the aftermath. The result, iron-rich fragments of the impactor, denser than the surrounding silicate rock, sink through a molten mantle the way a stone sinks through water, rather than floating like driftwood. Over time, as the mantle cooled and convection currents shuffled everything around, That dense material would migrate and settle into large, coherent masses sitting just above the core mantle boundary, resisting being fully mixed in, the way oil resists mixing into water even after vigorous stirring. The models predicted structures in roughly the right location, at roughly the right depth, at roughly the right mass, exactly where the LLVPs are, exactly the size the LLVPs are. The team, led by Yuan and Arizona State University's Ming Li, published their findings in the journal Nature on November 1, 2023. The conclusion: portions of Theia likely never left Earth at all. They are still down there, essentially fossilized in the deep mantle. You have been standing on top of a dead planet your entire life. Why this isn't just a curiosity? Here's where the story stops being a neat trivia fact and starts being unsettling. These blobs are not inert relics. They sit directly at the boundary between Earth's molten outer core and its rocky mantle, the single hottest, most turbulent interface in the solid part of the planet. That boundary is also where mantle plumes are thought to originate, slow-rising columns of unusually hot rock, sometimes called mantle superplumes, that push upward through thousands of miles of solid mantle over millions of years before finally breaking the surface as volcanic hotspots. Iceland sits on top of one. Hawaii sits on top of another. So does the volcanic rift running through East Africa. Some researchers now suspect these plumes originate specifically at the edges of the LLVPs, meaning the boundary of a dead planet's remains may be acting as a launch point for the plumes that built entire volcanic island chains. If that connection holds up under further study, it means a world that died 4.5 billion years ago may still be quietly shaping which parts of Earth erupt today. Not as some faint ancient echo, but as an active, ongoing geological process, running in the present tense. The ground under your feet may, in a very real and literal sense, still be partially foreign. And the story deepens further when you look back at the Moon itself. A 2020 isotope analysis of Apollo lunar samples found that Moon rock's oxygen isotope ratios were more varied than earlier studies had suggested, and crucially, not varied at random. Samples believed to originate deeper in the lunar mantle, further from the surface mixing that followed the impact, showed values that diverged more sharply from Earth's than surface samples did. The interpretation: those deep samples are a truer, less diluted reflection of Theia's original chemistry before it collided with anything. And what they hint at is striking, that Theia may have originally formed farther from the Sun than Earth did, in a different thermal and chemical zone of the early solar system entirely. Not a twin planet that happened to be sharing our orbit, a genuinely foreign world that wandered in and never left. What we still don't know. To be clear about where the evidence actually stands, this is a strong, well-modeled hypothesis, backed by seismic data and impact simulations. It is not yet a directly confirmed fact, and honest scientists treat it that way. Nobody has drilled 2,900 kilometers down and pulled up a rock sample labeled Theia, nor will anyone with any technology we currently have. The evidence here is entirely indirect. How fast waves travel through a region we will never physically touch. The leading rival explanation is still on the table too. It's possible the LLVPs are simply an unusually dense, iron-enriched pocket of primordial Earth material that has survived since the planet's formation, having never fully mixed into the surrounding mantle through billions of years of slow convection. Chemically odd, but native, with no impactor required at all. Distinguishing between ancient piece of Earth and ancient piece of another planet, using only seismic wave speeds from thousands of miles away, is extraordinarily difficult, and researchers on both sides of this question would tell you the case isn't fully closed. What tips the argument for many geophysicists is how well the numbers line up once you assume the impactor explanation. The location matches where dense impactor material would be expected to settle after billions of years of sinking. The mass matches what a Mars-sized body would be expected to leave behind after the lighter material vaporized into orbit to form the Moon. And crucially, the impactor hypothesis is the only one of the two that also explains a completely separate observation: the Moon's own iron deficit, using the exact same event. One collision, one explanation, two independent puzzles solved simultaneously. That kind of unifying fit is exactly what makes a hypothesis compelling in science, even before the final, unambiguous proof arrives. The planet you're standing on. So the next time you look up at the moon, consider the full shape of the story. That bright disk in the sky is only half of what's left of Theia. The lighter half, the part that vaporized outward and had time to cool into rock in orbit. The other half, denser and heavier, never made it off the planet at all. It fell the other way, straight down into the deep Earth, where it has sat for 4.5 billion years, slowly steering the very volcanoes that shape the surface living things now call home. Earth and the moon were never really two separate stories running side by side. They're both debris from the exact same catastrophe, one half flung into the sky where anyone with a clear night and a pair of eyes could study it for millennia, the other half buried at the bottom of the world, invisible, waiting almost 50 years for a scientist in a seminar to finally connect the two. We didn't just inherit our moon from that collision billions of years ago. We may still be living, quite literally, on top of the wreckage, and somewhere out past the orbit of the moon, drifting through interstellar space, entirely unrelated to any of this, there's a visitor that arrived from a different star system altogether. That's a story for next time.